Is that correct? Shows what was it? It's something like potassium permanganate. Or maybe not. Potassium permanganate, hydrochloric acid, and sodium nitrate. Does that sound familiar? Yeah. Okay, potassium permanganate plus hydrochloric acid plus sodium nitrate. So I heard this one already, KMNO4. KMNO4 is potassium permanganate. Hydrochloric acid should be easy. What's that? HCl. And sodium nitrate. NaNO3. Okay. So these look to be double replacement style reactions, right? AB plus CD. We could do it. What we could do is we could do it like this: A, B, C, D, E, F. And so what we could do is AB plus CD, and then AB plus EF, and then CD plus EF. In other words, we could try all combinations. Basically, what metathesis is, what is metathesis? Favorable ion combinations. So what we can do is we can just list the ions here. What are the ions that we got? Well, we got, for the cations, we have potassium, H plus, Na plus. We can set up some kind of grid like this. For the anions, we have permanganate, we have chloride, we have nitrate, like this. That's something we could do. Do you see some favorable ion combinations here? Did we already do this?
We did it with iron sulfate.
No.
So that's potassium.
Oh, all right. Iron 2 sulfate. Sorry, that's my mistake. We did it with iron 2 sulfate. FeSO4 plus HCl plus NaNO3. Is that right? All right. And did we do the double replacements also? For example, did we do the FeSO4 plus the HCl?
Yeah.
We did that? And did we talk about the leveling effect? Yes? All right. And so we could do this. What's going to form is iron 2 chloride plus sulfuric acid. We know because of the leveling effect, the sulfuric acid and hydrochloric are the same. Or we could do it with sodium nitrate. We take FeSO4 plus sodium nitrate. So this is our AB plus CD, and then we try AB plus EF. This is going to give us iron 2 nitrate and sodium sulfate. That's not really going to do much. So that's AB plus CD, AB plus EF, and then let's do a CD plus EF. It would be HCl plus sodium nitrate. If we do HCl plus sodium nitrate, what are we going to get? We're going to get nitric acid. But the situation with nitric acid is we compare HCl and nitric acid. What do we know about the leveling effect? The leveling effect is going to say HCl and nitric are going to be the same. So there's no driving force for that. So different ways we could set up metathesis reactions. We could set up like a grid. A grid is just to figure out what all the cation anion combinations are and see if any are favorable. Or we could just set it up as multiple double replacements since we have 3 AB type compounds. Does that make sense? But the end result is that there's going to be no precipitate, and therefore there's no driving force from precipitation, there's no stronger to weaker acid, and there's no gas formation. So basically there's no metathesis reaction. Sorry, let's get rid of this. And so, etc. No reaction. I have to say no reaction for metathesis because we're only testing for one type of reaction, and that's favorable ion combinations. What other types of reactions do we have? We have acid-base and redox. So if there's no metathesis reaction, then we should look for which one next. Actually, did we do this or we didn't do this yet? The acid-base. We did it? Oh, okay.
You said that there was another one. There's another.
Yeah, and so the acid-base reaction was this one, right? The hydronium plus sulfate yields HSO4 minus plus water. Is that what we have? Okay. There is a driving force for this. And so we do have acid-base. But there's still one more type of reaction that could potentially take place, and that one more type of reaction is redox. And so now look for redox, or potential redox. I look for potential because the more familiar you get with these chemicals, the more you start to see certain things. Like, you know, a lot of these species are on the redox chart. So there could be a potential redox reaction that occurred here, and some of those species are fairly strong. And so when we do the redox method, the first step is to do what? This is going to be the chart method. The chart method, because this does not fit single replacement form. So what's the first step? Chart method. Inventory. So we kind of already inventoried it for this, the Bronsted. So we'll just rewrite the inventory, which is, we'll just use the same inventory. It's going to be Fe2 plus, SO4 2 minus, H plus. For redox, I like to write H plus rather than H3O plus. H3O plus is more common in Bronsted acid-base reactions, but in redox, we'll leave it as is. Cl minus, Na plus, NO3 minus, and one more species, which is H2O. Okay, then we're going to use the chart to determine. And so basically for the chart method, you don't need to know any chemistry. You could do this method with zero chemical knowledge, except for this. You know, when we inventory it, we need some chemical knowledge here to figure out what ions it breaks up into that. But from here on out, you need zero chemical knowledge to figure it out. Because all we do is we just consult the chart, see where it is, which side it's on the chart. And so let's take a look at the first species, which is Fe2 plus, iron 2 ion. And so if we could just start off on the chart here on the left side, go down. What is iron 2? So what's this? Let's just rename. You know, getting some familiarity with the chart will increase speed. You know, it's like if you use this chart for the first time on the test, everybody who does something for the first time is going to be slow, you know, usually. Especially with an unfamiliar chart like this. But the more familiar you are, the faster you'll be because you'll already know approximately where those species are. And so what you should do is, you know, you don't have to do this every day, but once in a while just go through and read them off like this. F2 is called what? Fluorine, ozone. This one we don't need to name. This is an unusual ion. This one we should name. H2O2 is called hydrogen peroxide, permanganate. These are the top 5 oxidizers on the chart. Permanganate's number 5. But it's permanganate with H+. We need H+ in a lot of these. You need H+ because H+ is critical for forming water. If water didn't form, what's water without H? Water without H is just oxide. Oxide is a pretty powerful base. It's not stable. What's this? Which is it lead 2 or lead 4 oxide? Lead 4 oxide. Each oxide is -2. You have 2 of them. That's -2. -2 gives us -4. And that means this is going to be +4. Cl2 is called Cr2O7, 2 minus. Dichromates, right? MnO2. Manganese 4 oxide. Sometimes this is called manganese dioxide, but that's naming it more like a molecular compound. This is also called desert varnish. It forms like a black coating on rocks. Yeah, Death Valley or outside of Las Vegas, there's lots of desert varnish there. But it's a very tough coating. It's good. Oxygen, iodate, bromine, nitrate, silver ion, iron 3. Is iron 3, is that okay? Iron 3 versus iron 2? No, it makes a big difference. Iron 3 versus iron 2, it's a big difference. So we can't use iron 3. You gotta keep going down. This is, why do we see oxygen twice? Talked about this a long time ago. Why do we see oxygen twice? This is deja vu. We just saw oxygen here, now we're seeing it here again. See, this is why one of the other things that you want to do is you want to answer these types of questions before the test, For example, why is oxygen there twice? You should know that before the test. What's this one? What? Iodine or iodide? Iodine, or iodine. We'll call it iodine. Copper 2, sulfate, tin 4, sulfur, hydrogen ion, lead 2, tin 2, iron 2. Here is iron 2. So iron 2 is what? Iron 2 is all those species we named are oxidizers or reducers? All those species are oxidizers. So iron 2 is an oxidizer. Let's continue on. You want to have a little familiarity with these because the next one here is zinc or zinc 2. Zinc or zinc 2 ion. This one's just zinc. This one's iron 2, but this is just zinc. Why is that? It's fixed charge. Just like this next one. Aluminum. Magnesium. Sodium. Calcium. And lithium. All those you have to add ion, the word ion on there, because there's no other indication. For example, iron 2, I don't need ion. Everybody would know iron 2 is an ion. It's got a 2+ charge. But if somebody's talking about zinc, they don't know if you're talking about zinc metal or zinc ion. So you have to have the word ion for these fixed charge ones. Lithium ion being the worst oxidizer, but lithium metal is the best reducer. So let's just go up this one just to get. This is lithium. This is. That one, that one's a little tricky here, because if we name this like a normal binary molecular compound, we'd call it dihydrogen monosulfide, right? But it's not. These compounds that are also acids are named using the ionic name. And so what would the ionic name for this one be? It'd be the hydrogen cation with a sulfide anion. So we'd call this hydrogen sulfide like a normal ionic compound. It's weird. And we wouldn't call it dihydrogen monosulfide. Now, if this were aqueous, what would we call it? Hydrosulfuric acid. Then, tin 2. Well, sulfite is SO3, so this must be hyposulfite ion? Is that correct? No, actually, sulfite is an SO3 2 minus. Sulfate is SO4 2 minus. This has no charge. Therefore, this is not an ion. This would be called sulfur dioxide. It's a neutral compound, binary molecular compound. So sulfur dioxide, copper, iodide. Didn't we see hydrogen peroxide before? Yeah. Hydrogen peroxide is like a top 5 oxidizer, but it can also be a reducer, but it's not a very good reducer. It's a much better oxidizer than a reducer, but nonetheless, we'd still consider it here. So hydrogen peroxide is one of those species that can go either way. Just like the next one. What's the next one? Iron 2. And so this is one of the big mistakes that people make is they'll see iron 2 just on the left side, but they didn't realize iron 2 is also on the right side, meaning it's both an oxidizer and a reducer. And so having some familiarity with the charge, with the chart can prevent this kind of error. The same thing like hydrogen peroxide. You know, how it behaves, whether it's an oxidizer or reducer, hydrogen peroxide or iron 2, depends on what you react it with. And so in some cases, hydrogen peroxide is an oxidizer, in other reactions it's a reducer. Depends on the reaction mixture. However, sulfate is only a oxidizer, but sulfate also requires one other species in there. So if we take a look at sulfate, where is sulfate? Here's sulfate. What else is required? H+. Now, do we have H+ available? We do. The H+ is coming from the hydrochloric acid here. And so it's all mixed together. So we got sulfate and H+ combined. That's going to be our oxidizer. Now, what if H+ were missing? If H+ were missing, then if H+ were missing, then can we form water? No. I mean, what's water without hydrogen? And so we have to form something else much less stable. So if H+ is missing, then its rank gets lowered dramatically. You know, if the H+ is missing, its rank gets lowered dramatically. But it's there. And it can come from any source, you know, wherever. In this case, it comes from HCl. But there's also H+ alone. H+ alone is an oxidizer. And so, that. Chloride is a I see chloride at the very top. Do you see it? Chloride is a reducer. What about, is it both an oxidizer and a reducer? No, chlorine, which is Cl2, is the oxidizer. Chloride, its conjugate, is only a reducer. So this is just a reducer. Sodium ions. So the sodium ions near the bottom. Sodium ions are oxidizer. Okay, then we saw nitrate up higher. Up there, do you see nitrate and H plus? Don't worry about the ratio. You know, it's a 1-to-4 ratio here, 1 nitrate for every 4 H pluses. It doesn't matter, we can balance all those things out later. All we need to know is that there's nitrate and there's H plus present. If there's nitrate and H plus present, that's a good combination for an oxidizer. There. So nitrate and H plus oxidizer. Now water, if we look at water, water's at the bottom here. Does that mean it's the worst oxidizer on the chart? It's at the bottom? You know, on the test, people come up and ask me about this all the time. On the exam, somebody will see, oh, water's down there, but they're confused because they don't remember water being the worst, or me saying water is the worst oxidizer on the chart. So they come up and ask me, you know, water's at the bottom here. Does that mean it's the worst oxidizer? And I say, I can't tell you. This is the examination. You're supposed to know this, you know. And so I send them back to the desk without an answer. But they're very confused. They shouldn't be confused because they should know that water is not the worst oxidizer on this chart. The worst oxidizer, I just said, was lithium ion. So what is water? Well, this is why I did this in a secret code. What's a secret code? The 3 dots. These 3 dots, which look like just the dots wherever else, those actually have significant meaning. All these other ones are just, it wasn't a clean copy, sorry. But these are significant because that's where water belongs. It belongs there. So of course, having familiarity with the chart means you're going to be much faster than somebody who's not familiar with this chart, who's thinking, now what do I do with water? How much time did that person spend thinking about water before finally coming up and asking me? Maybe not much, or maybe a lot. Kind of a waste of time, though. So water is an oxidizer, and we can position its strength somewhere. Aluminum ion and zinc ion. But we also know that water is also this is another question I get asked during tests. They see water here and they see water here, and they come up and ask me, which water do I use? I say, I can't tell you that. This is examination. You're supposed to know that. Which water would you tell them to use? See, this is the stuff they notice only during the test, but before they didn't notice it because they probably didn't look at the chart before the test. I mean, that's what it was apparent to me. Or these waters. Should I use this water? Why not use this water? Why not use this water? It's because, do you have NO gas present in the inventory? This water is combined with NO gas. However, this water here I can't use either because do we have iodine? No. This water, we don't need anything else. This is just water. So should I go ahead and use this one? Or should I use this one up here? This water seems to be all by itself. So which one would you use? This one down here or this one up here? You tell me. The bottom one, yeah. So if you told them the bottom one, then they would have been okay. Why the bottom one? Yeah, this one is not going to be as good. This one's better. This one's stronger. You use the stronger one right The strongest one is gonna be the one that's closest to lithium. So this is it. And why is this one stronger? And this one's stronger because you're right. This one makes hydrogen peroxide. This one makes oxygen. Oxygen's more stable than hydrogen peroxide. That would be the reason why. And so actually water turns out to be both an oxidizing agent and a reducing agent. Okay, what's the next step in the chart method? Not acid and base, we're doing redox now. Yeah, we want to find the strongest. How many oxidizers are we dealing with? We're dealing with 1, 2, 3, 4, 5, 6 oxidizers. So which one of the 6 is the strongest? Well, what's the strongest on the chart? Strongest on the chart is fluorine, so let's go down. Which one will be strongest? Let's see. The strongest will be nitrate. So this is it. Nitrate and H+. Okay, do the same for the reducing agent. Pick the strongest, and then continue. Is it coming back to you, the steps? Okay, and then continue with this. Or see if I have it. Yeah. You should have enough there. So then pick the strongest reducing agent, and then I'll be right back.